Do you know how to model a solenoid or an inductor with multiple turns in COMSOL? Most people get stuck here. Either they don't know how to set up the multi-turn option, or they cannot connect the coil to a circuit correctly. In this video, I'll solve that problem for you. We'll go step by step, first building the geometry, then setting up the Multiturn coil, and finally connecting it to an electrical circuit. Stick with me because I'll also share some pro tips that will save you a lot of trial and error. Okay, I have opened my COMSOL Multiphysics. Go through the model wizard. First, I select 2D Axisymmetric. Under AC/DC and magnetic fields, select MF for your physics. And for our first simulation, I select the stationary static. Click Done. In the geometry, we need two rectangles, one simulating the surrounding air and the other one our coil. Let me first set the length unit to centimeter. Go to Geometry tab. I deselect the sketch mode and select the square. I set the side length to 100 centimeter and set the base as the center r equal to 50 and z equal to 0. And in this case, the line of r equals 0 becomes my axial symmetry line. Now I click on rectangle. I need a rectangle maybe with a 2 centimeter wide and 40 centimeter of height, and I set the center at r equal 10 centimeter and z equal 0. This rectangle is our coil and the larger square is the surrounding air. Notice how I always enclose the coil in air. Missing this step is one of the most common mistakes beginners make. You can also come under this square and set layers, for example 5 centimeter to the right, bottom and top, and set these layers to infinite element domain, which I have already explained in my previous video. The only material that we need is air. I go through recent materials and add air to our simulation. Then I close a material window. We need only air because we inject current through the Multiturn coil option through the physics. Let me explain. The coil domain represents many turns carrying current, but we model it as a homogenized material region filled with air. In fact, we set the conductivity, cross-sectional area, and so on in the physics. Okay, the material section is done. Right-click on your physics, magnetic fields, and select the coil option. First, you should select the domain that includes your coil. I select my rectangle. Very well. Here are the options. If you double-click everywhere, you can just maximize your window. I set the material type to solid. The coil name can be 1. Under the conductor model, I select homogenized multi-turn instead of single turn coil. It says that region consists of several turns. Because you have only one domain, it doesn't matter if you check the coil group. And I set the coil excitation to current, and I want to feed 1 ampere through this area. This is the important part. This is the number of conductors in that region. For example, I set it to 1000. This is the conductivity of the wire that has been used to wind the multi-turn coil. This is the conductivity of copper. I let it be. And this is also the cross-sectional area of the wire, which equals to 1 square millimeter. And why is this important? Because the cross-section, conductivity, and the number of turns determine the equivalent resistance of your coil. In other words, it determines the coil dissipation or its quality factor. If you use a smaller cross-section or lower conductivity, the coil resistance increases and your results will change dramatically. Okay, the other things can remain at default. A normal mesh suffices for our purpose, and under the study, click on Compute. Okay, here are the results. The magnetic flux density is much stronger inside our coil or solenoid and weaker outside. Also, the field lines show a nearly uniform field in the core area. You can just double click everywhere. Let me maximize this one. And this shows the magnetic flux density here. And you can see that everywhere the amount of magnetic field is more or less 2.8 millitesla. Shows that we have a uniform magnetic field, which is the case inside a good solenoid. You can also watch this in 3D. Just come here under the magnetic flux density. Just let me, under the data set, remove the surrounding air, right click and selection, and instead of entire geometry, I set it to domain and set this domain. Therefore, I can see my coil only without the surrounding air. Okay, stay with me if you want to learn how to connect this coil to a circuit, as I'll walk you through it in the 2D modeling. Okay, let me switch to 2D model. I've gone through the model wizard, select magnetic field, 2D and stationary. I also plotted a little bit of my geometry. This is the surrounding air, and this rectangle models the cross-section of one of my coil faces. Okay, let's look at this sketch. We have a solenoid here. If we cut the solenoid, because we are drawing it in 2D, we see only two faces, the right and left face of our solenoid. If this would be the current direction in our solenoid, we can notice that in the right face the current is inward and in the left face the current is outward. In other words, the direction of current in the two faces of a solenoid in 2D should be reversed. So in the 2D we must model both faces. For that I just come under the geometry. I do not want to give my dimensions again. Therefore, under the geometry tab and under transforms, I select mirror. I want to mirror this face with respect to the origin. I select this domain, I want to keep it, and the line of mirror goes through the origin, and this is the normal vector to that line. If you click on build selected, the second face of your solenoid is formed. Okay, our geometry is finished. We can also set the infinite element domains, but I just skip that part. The material is air everywhere. Again, we don't need anything else. And now come under the magnetic field, right click and select your coil. Select the first coil, and again I set the type to solid. The name could be 1, homogenized multi-turn. I set the coil excitation to 1 ampere and set the number of turns to thousands, just like before. Now I also want to define the second phase of my solenoid. For that, I just right click on coil and select duplicate. Here I clear my selection and I select the second phase of my coil. The current direction in this part should be reversed from this one. In COMSOL, in a 2D, a positive current means outward toward you and the negative means inward. So if I want the current in this part to be reverse of the other part, I should set the coil current minus 1 ampere. This is one of the most critical steps. If you forget to reverse one coil phase, your simulation will give nonsense results. Okay, everything is ready. Just compute your study and see the results. Again, you can see a uniform magnetic field inside your solenoid and a much weaker magnetic field around. If you want to set the in-plane dimension of these coils, you can just set it under your physics. Here, the out-of-plane thickness is set to 1 meter. Okay, if you want to see the current distribution over your geometry, right-click on results, select the 2D plot. Under that, select the surface. Replace expression, magnetic fields. Under current and charge, you have a current density, and I want to see the current density in the Z direction, perpendicular to my surface. Select that and click on plot. You can see that I double clicked here. Let me clear that. You can see that the current density is positive in the right leg and it is negative in the left leg. Okay, let's learn another trick which simplifies the modeling of a coil in 2D. I want to model both faces of my solenoid under only one coil option. I come here, first I remove my second coil. Under coil 1, I select my second face. and come down and check the coil group option. It means that the current is the same in all my domains and all the selected domains act as a single coil or a coil group. Now we should tell COMSOL that the current in one domain is reversed with respect to the other one. For that, right click coil 1, you can find an option here, reverse current direction, click it, and I now select my second phase. In this case, the current in the second phase is reversed with respect to the first one. I recompute my model, and if you check, you can see that nothing has changed in my model. If we check the current distribution, current density, you can see that the value of the current is same as before. Okay, now I want to excite my coil with a sinusoidal current. For that, you need only come here under coil current and define a sinusoidal current. I type sine of 314 multiplied by t, which is the 50 Hz signal. Now you need a different study because we only have a stationary study, but now we need a time dependent. To add a second study, right click study, here under study steps, time dependent, select time dependent. You now have a time dependent study. I set the time unit to millisecond and I want to study my model till 100 milliseconds in 1 millisecond step. Click replace. Everything is ready. Before computing your model, you should disable the stationary study because at the stationary study this parameter t is unknown for COMSOL and you get an error. Okay, let's compute our model in the time domain to see what happens. Okay, this is the distribution of magnetic flux density in our coil. Now I want to show you that the magnetic field here is also sinusoidal. For that, I pick a point in my graph and then plot the magnetic field of that point versus time. Let me just minimize global definition, that's better. Right click dataset, select cut point 2D. I set my x and y 0 and 0. Which is the origin or the center of my solenoid. Right click results again, pick a 1D plot group and right click, select point graph. Point graph means that I want to plot a variable or a parameter which is relevant to a point in my geometry. I select that. Under the dataset, I select my cut point and here under replace expression, magnetic fields, under magnetic, here we have magnetic flux density. I want to plot magnetic flux density in the y direction because I already know that the magnetic field inside my solenoid is in the y direction. The x-axis is automatically set to time. Click on plot and now you can see that the magnetic field also have a form of a sine because the excitation current is a sine. Okay, now I want to see the change of magnetic field over my domains versus time. I need to animate my magnetic field. For that, right click export. And here you have animation option. If you select file, you can directly export your animation. If you select a player, you can first see your animation in the COMSOL. Select player. I want to animate this plot versus time, which is the magnetic flux density. Therefore, under animation, under subject, I select this diagram. The target is a player, which means that I want to see the changes in the software. Because I have studied until 100 milliseconds in 1 millisecond steps, I set the number of frames to 100. You can here change your frame or set your frame number to see a specific frame. Here you can also set your time selection. I have set it to all because I want to see all 100 milliseconds. Okay, everything is ready. Let me maximize my window and now I click on play. Now you can see the change of magnetic field versus time as an animation. It's perfect for visualizing your results for presentation. Okay, let me minimize it and stop it. If you here change your target to file, you can select your file type and also your file name under browse, and if you click on export, you can then find your file in the given direction. Now is the point where I want to explain how to connect this coil to an electrical circuit. Let's see our circuit first. Here is the circuit that I want to model. I have a source that can be DC or AC. In series, I have a resistor, and then I have an inductor, which is my solenoid, which I have modeled in my 2D geometry. In the terminology of electrical circuit in COMSOL, for each component that has two connections, we have two names, P for positive side and N for negative side. We have 3 nodes in our circuit. The ground node has been automatically set to 0 in the electrical circuit. I name this node as 1 and name this node as 2. Now I know that my solenoid should be placed between node 2 and 0. Let's get back to COMSOL. I want to add electrical circuit module here. Right click component, select add physics, and under AC/DC, double click electrical circuit. Let me close this. This is my ground node, which is 0. First, I need a source. Right click and select voltage source. I let it be a DC source with a 1 volt amplitude. Here you can see that my source has been placed between node 0 and 1. The positive side has been connected to node 1. The negative side is connected to node 0. Now I need a resistor. I picked a resistor. This is P and N, the both sides of my resistor. Here you can see that the P side is connected to 1 and the negative side is connected to 2. I set the P to 1 and N to 2. Now I should define my solenoid in the circuit. For that, I first should come back to coil option and set the coil excitation to circuit voltage. Just look at what COMSOL says itself. It says connect to external UVSI in the electrical circuit. It says that if you want to define or connect this coil in the electrical circuit, you should define it under an external UVSI. I come here, right click my physics. Here under external couplings, I select external UVSI. And here, if you select, you see that the COMSOL automatically recognize coil 1. That's very good. Now we should define the nodes. Here we can see the positive side is connected to 2, the negative side is 0. 2 and 0. And now everything is ready for our simulation. 100 milliseconds is okay. I just compute my model again. Okay, our result is ready. Let's see the current of my circuit versus time. For that, I add a new 1D plot group. Right click and select global. Global means that I want to plot a variable or parameter which is not confined to a point or a line, boundary, or a domain in my model. Select global, replace expression under electrical circuit, under device. If I see the current through my resistor, I can check the current through the circuit overall because all the elements have been laid in series. Open it and select current through device R1. The x-axis have been automatically set to time. You need only to click plot. You can see the change of current versus time here. To see it better, I just come back and set my resistor to 1 ohm because the resistance was very high. Let's recompute our model and let's check our current. This is the current behavior in an RL circuit. The same thing that we have expected from the circuit, that the current starts from 0 and goes up in an exponential form until it reaches a steady state. Just as a hint, from the steady state value, you can estimate the equivalent resistance of your coil because the only thing that determines the steady state current is the resistance in our circuit. Okay, let's excite our coil with a sinusoidal source. I just come back here under the voltage source and define it as a sine source. I recompute my model and let's check my current. Okay, that's very interesting. You will see a sinusoidal response with a transient DC offset on it. This transient is not a bug, it's real physics. It depends on the ratio of X to R of your circuit and the instant when voltage is applied. If I change my voltage phase by 90 degrees, for example type plus pi divided by 2, you can see that the transient decreases very much. Click on compute. You can now see the transient nearly disappears, exactly as we expect from circuit theory of an RL set. Okay, that's it for today. You just just learned how to build a solenoid in 2D and 2D Axisymmetric, how to configure the multi-turn coil option, excited with current or voltage, and connect it to an external circuit inside COMSOL. In my next video, I'll take this even further. I'll show you how to add a magnetic core to your inductor. First linear and then a saturable core. And right after that, I'll cover how to model the same solenoid in full 3D. So if you don't want to miss this advanced tutorial, make sure you subscribe now, hit the like button, and turn on notifications. Also, check the descriptions below for the simulation file from this tutorial. Thanks for watching, and I'll see you in the next tutorial.